All right, so section 5.2 has to do with inner product spaces, and just because it's not end of the day is enough. Right now it's hailing outside. I don't know if you can see it. So it's a very ominous way to introduce inner product. So let's see. This is also the mechanism that I had helped build in order to provide a support for my camera. Excellent. So let's see. An inner product is a general form of the dot product. So we are familiar with one type of inner product, the Euclidean inner product, and we call it the dot product right now. So in general, an inner product is defined as a product, a way to multiply vectors that follows these four axioms. So luckily, you know, in the vectors that you pick are supposed to be in a vector field, in a vector space V. So U and V are in a vector space V, and C is a scalar. Okay, so we have this new definition. So usually the way we define the dot product of two vectors is we take the components and we multiply them, right? So you have vector U, U1, U2, vector V, V1, V2. And usually there's no 2 there, right? So this is a weighted product. So we have to show that this product is an inner product in R2. So we have to show these four axioms hold in general. So we're going to first show axiom 1. Axiom 1 would have you begin with the left-hand side and end with the right-hand side. So we are going to start, we're going to assume U and V are these guys. So we are going to start with the definition of how this is made. So another way to do this is to say U1, U2, right? That's vector U. Product with V1, V2. And we're not going to multiply them with the Euclidean product that we're familiar with. What we're going to do is we're going to multiply it in this way. So we're going to say this is U1, V1 plus 2, U2, V2. All right, so my end goal is to have these U's and V's switched. Because U1 and V1 are real numbers, you can say, well, this is the same as V1, U1. The real numbers are commutative. 2 times V2, U2. And so this is really the definition of the product as defined in this way of V1, V2 with U1, U2, right? So if we go from here to here, this is exactly applying the definition of your inner product. So you really showed that this is the same as V and U in general. So again, to prove axiom 1 for all vectors in R2, we cannot plug numbers in. You have to use a general vector like this. Axiom 2. Axiom 2 says to do this. So we're going to start with the left-hand side. I need another vector W. So here's my vector W made with W1 and W2. And so I'm going to start with U, V plus W. And that means U1, U2 dotted with, I'm just going to add V and W in the next vector here. So it's V1 plus W1, V2 plus W2. This is because I added V and W here. So now I'm going to apply this inner product definition, and I am going to plug in these values for it. So that means this is U1 times V1 plus W1, right? The first two multiplied together, plus 2 U2 times V2 plus W2, right? So plus 2 times the last two components multiplied together. That's this and this. And so now my end goal is to separate this into two vectors, uv and uw. So I'm going to distribute this and pull u and v aside and u and w aside. So this is going to become u1v1 plus u1w1 plus 2u2v2 plus 2u2w2. So now I'm going to pull this apart into the components for u and v. So u1v1 plus 2u2v2 plus u1w1 plus 2u2w2. This here is the definition of the product of u and w. So this is going to be u comma w. This here is the definition of the product u and v. So this is going to be u v. So I showed that axiom 2 holds. I showed axiom 1 hold. For axiom 3, again, we have to show this in general. We have to show that the inner product of u and v is the same as distributing the constant to just one of the components. So we're going to start with the left-hand side, and we're going to end with the right-hand side again. So I'm going to start here, and I'm going to say C times UV is, of course, C times, this is how we do product now, U1V1 plus 2U2V2. I'm going to distribute my C and next I have to pull this apart into multiples of U and V by itself. So I can insert parentheses around these. So these are all real numbers. 2 times CU2 V2. So then I can say, well, these two got multiplied with V1 and V2 to get this, right? So this 2 is part of the way that I defined the inner product space there. So that 2 was part of my definition. So this is C times U product with V. Now, for axiom 4,